Hi everyone, this is Chen Zhou, a CS PhD student at the University of Chicago. Thanks for tuning in my presentation on PSACS. It's a highly parallel shuffle accelerator on computational storage. This is a joint work with Hui Zhang and Yang-Suk T from Samsung Semiconductor Inc. and Professor Andrew Chen from University of Chicago. First, what is a shuffle? Shuffle is an indispensable process in distributed online analytical processing or OLAP systems. Shuffle enables parallelism exploitation via multiple nodes. In this word counting example, the map task carrying out the aggregation in the second stage were able to execute in parallel in each node because of the shuffle at the end of the first stage. The shuffle task distributes the same words inside a single node to allow later parallel aggregation. Shuffle is usually a three-step procedure. First, records are partitioned, which determines records' destinations after shuffle. And then, records going to the same destination partition are grouped together. Finally, grouped records in each node are fetched by their destination. The group step aims to increase network transfer efficiency during fetching through increasing transfer block size. It is the most challenging step because it performs data reorganization among a huge working set with scarce data reuse opportunities, leading to cache thrashing, spilling into memory and storage. These memory behaviors usually make shuffle a bottleneck in OLAP workloads. We performed profiling with 4 nodes running TPCH queries with scaling factor 1000 under Spark to quantify the shuffle bottleneck. As we can see from the result figure, shuffle may take 1/3 latency of an OLAP query because of the challenges we mentioned in the group step. This motivates our designs of PSACS to address the shuffle bottleneck. PSACS accelerates shuffle, especially the partition and group steps in distributed online analytical processing systems through computational storage, where computation is introduced inside storage. It allows us to completely offload shuffle tasks and its data traffics inside storage, reducing the traffics between CPU and storage, as well as liberating CPU and memory for other OLAP tasks. Further, PSACS microarchitecture exploits multiple levels of parallelism in shuffle workload and customized memory hierarchy for efficient shuffle memory accesses. With these features, PSACS achieves 5 times kernel-level shuffle throughput improvement and on average 23% end-to-end OLAP query speedup. We will now dive into detailed PSACS acceleration approach for each shuffle step. First, for shuffle partition step, we opt for a hash partition approach for its generality for not requiring an ordering relation. Different from hash approaches used in cryptography, collision resistance is not a priority. Rather, each partition should get a near-even allocation of shuffling records. For additional evenness, we applied a variant of fault hashing, which additionally zigzagged the input as shown in the figure. Our approach for group, the most challenging shuffle step, differs from the existing work. The previously used approach, bucketing, maintains a bucket for each destination partition to temporarily hold records for corresponding partition. However, bucketing features linear scaling between on-chip memory capacity requirement and the number of partitions needed to support. This is not feasible in a distributed OLAP systems that may require thousands of partitions for thousands of cores. As a result, we opt for a sort-based group approach. Records are grouped together through sorting records by their destination partition IDs. This approach features fixed resource requirement for any number of partitions. We further apply optimization of only sorting record pointers. Sorted record pointers would be used to gather the records efficiently from customized scratchpads later to finalize the grouping. Putting it all together, the figure here shows the microarchitecture of PSACS. We would draw in green the shuffle progress of the word counting example to help explaining it. First, there is a finite state machine module that controls the overall shuffle process. The FSM would trigger the prefetch of data to be shuffled into the reader, which manages a custom scratchpad that aligns table data and accepts random access. During this prefetch, the shuffle keys are further streamed into partitioner and get mapped via our zigzag folding hash to partition IDs. The sorter further sorts the partition IDs along with corresponding record pointers. Here, we exploit subtask parallelism by concurrently performing prefetching, partitioning, and sorting. Gather would accept the sorted record pointers and use them to random access reader's scratchpad to piece together the full record. Here, with the alignment support by the customized scratchpad in reader, the whole record of multiple bytes are gathered in one cycle, exploiting the data level parallelism. Finally, writer would buffer records from gather and handle the DRAM access protocol to write the shuffle results to computational storage DRAM. For the ease of evaluation, we implemented PSACS on Samsung Smart SSD, which embeds an FPGA into a solid-state drive. The results should be able to generalize to different computational storage platforms that feature an FPGA. We adapted on-site merge sorter to achieve ON log n sorting in our sort module. The resource utilization for implementing our PSACS accelerator is shown in the table. We are mostly limited by the on-chip memory resources from further scaling out our PSACS design in the FPGA. We first compare PSACS kernel-level performance with hand-optimized single-thread software shuffle using sort or bucket-based grouping. PSACS is around 5 times faster than its software counterparts because of its exploitation of subtask and data-level parallelism. We further consider system-level performance, including data preparation and results writing back along with shuffle. Here, software methods can employ up to 32 threads for concurrent shuffle tasks, where PSACS, limited by resources available in the FPGA of a smart SSD for further scaling out, can only exploit system-level pipelining to absorb data preparation and the results storing latency into the latency of a single-thread shuffle acceleration. Despite that, PSACS still outperforms 32-thread software methods by around 20%. If we look at the CPU utilization between methods during shuffle, PSACS achieves more than 20 times CPU utilization reduction by offloading shuffle to computational storage. This liberates CPU and memory for subsequent map tasks and translates to, on average, 23% end-to-end speedup of TPCH queries in evaluation. PSACS learns from, builds upon, and advances this amazing related work. To summarize, we propose PSACS, the first shuffle accelerator addressing shuffle bottlenecks of OLAP systems. PSACS employs rising computational storage paradigm to confine shuffle traffics inside storage, exploits multiple levels of parallelism through hardware acceleration, and utilize custom scratchpads for high-throughput, low-latency accesses during shuffle group gathering. With these features, PSACS delivers 5 times throughput at the kernel level and on average 23% end-to-end OLAP query speedup. Thanks a lot for coming for my talk, and I'm happy to take any questions.